Okay, so we've developed sort of a couple postulates from the perspective of stability. We want to use those postulates here to develop some restrictions on the yield surface. So those restrictions are going to be the shape of the yield surface and also the direction of the plastic strain increment. So in this lecture, we're not actually going to do that. We're going to develop an additional postulate that we'll use to do that. But I want to give you a little bit of a roadmap to where we're going. So let's go ahead to start with and consider a stress cycle. Okay, and let's just plot this in, let's say, stress space. So there's our axes. Here's sigma ij and some other sigma ij, right? And maybe we have some stress surface that looks like this, right? Doesn't really matter. We're gonna start at some point inside the surface that we're gonna call sigma A. Okay. We're gonna load up along some path. It doesn't have to be straight up to this location on the yield surface that we're gonna call sigma bar, and then we're gonna keep on loading. So let me draw arrows for the direction that we're loading. Going to keep on loading, which will of course change the yield surface in some fashion, right? We're not even going to specify how. We're just going to say it changes it. It must do some sort of expansion or drag it or some combination thereof. There, that's our new yield surface. And on this yield surface, this location is going to be sigma bar plus d sigma. Okay? And then from that location, we're going to have a trajectory that takes us back down to sigma A. Okay? So let me write down the sort of the four steps here that we want to look at. So number one, we're going to start inside the yield surface at sigma A. Okay? So that's the first location. Then we're going to follow some load path. To the yield surface at sigma bar. Okay. And then in step 3, we're going to deform plastically. Okay, so we're going to deform plastically up to the stress sigma bar plus d sigma. And then finally, we're going to return elastically to sigma A. So return elastically to sigma A. Okay, so now we want to define a couple terms. So the first, let's just say here's the first term. We'll have some term that we'll call epsilon P, and I'll put an A on it. So epsilon PA, just to remind you that this is the plastic strain that accumulated prior to beginning the stress cycle at sigma A. Okay, so this is equal to the plastic strain that was produced prior to the cycle. Okay, and then during the cycle, from sigma bar up to sigma bar plus d sigma, we are going to accumulate potentially a plastic strain increment. Okay, so this is the additional plastic strain that's produced when we arrive at sigma bar plus d sigma. Okay? So now let's go ahead and think through sort of each step of the process. Okay, so let's first look at from sigma A up to sigma A bar. Okay, from sigma A to sigma A bar, we know that we're inside the yield surface so that there's no plastic deformation. So this is just elastic loading. Okay. Well, we know how to represent that. That says that our total strain epsilon at any time in this spot is some component of the elastic plus whatever the plastic was. So we call it, right, epsilon PA. Which we could write, if we wanted to write this now with Hooke's law, we would write that that's the compliance matrix S times let's say sigma, right, during this load step, then plus whatever the plastic strain was, right? Okay, so let's go ahead. We can call that equation 1. Okay, now we want to look at the next stage, right, from sigma bar up to sigma bar plus d sigma. So let's say from sigma bar to sigma bar plus d sigma. Okay. We also know what this looks like, right? This still looks very similar to 1, except now we have an additional plastic component, right? So we have an additional plastic strain. Okay, so we would write this then as the total strain is still equal to epsilon elastic plus epsilon plastic, right? But at the point of plus an additional plastic strain increment d epsilon p. Okay, we'll call that equation 2. And then we have the unload now from sigma bar plus d sigma back to sigma A. I should keep my superscripts and subscripts the same. Back to sigma A. Okay, it's all elastic again. Okay, so we would go back and write that epsilon is equal to epsilon elastic plus epsilon plastic original plus d epsilon plastic. I should make those tensors, not vectors. Okay, I'll call that equation 3. So we want to apply postulate 2 from the previous lecture, which, if you remember what that said, it said that the integral around on some stress path of epsilon ij d sigma ij would be negative semi-definite, so less than or equal to 0. Okay, so that's the postulate we want to apply to this load step. So here we go. There's the integral now from epsilon ij times d sigma ij. We're going to have the first step, which goes from sigma ij A up to sigma ij bar. And we already said that that looked like epsilon elastic plus epsilon plastic. Okay, that's the strain, times d sigma ij, plus the next step, which is sigma ij bar up to sigma ij bar plus d sigma ij. And that, we said, looked like epsilon elastic plus epsilon plastic plus d epsilon plastic, and that changes, that grows finally until we get to d sigma, and that's d sigma ij, right? And then there's that last term, which is the integral then from from sigma ij bar plus d sigma ij back to sigma a, right? And we said that was just back to now the elastic strain plus the plastic strain okay, plus the plastic strain increment, which in this case is not changing, but in this case it is, that quantity times d sigma ij. Okay? Let's call this equation 4. Okay, so in the above, let's just note this. In equation 4, we know that epsilon PA is constant, right? Right, that's the plastic strain that we had before the increment, so that doesn't change. So if we integrate a constant around a curve, so the integral around any curve of a constant, epsilon PA d sigma, is identically 0. Okay? So that's equation, we'll call that 5, right? So that takes care of this term, and this term, all three of those terms. A couple other things that we need to note, right? Because the complementary strain energy is recoverable for the elastic case, because the complementary strain energy is recoverable in the elastic case, okay, then we can also say that the integral over epsilon elastic d sigma is also equal to 0, right? So it's a conservative load, right? Okay, so let's see what that leaves us with now. If we would write that now, so let's just say substituting equation 5 and 6 into 4, what are we left with? That says that the integral of epsilon ij d sigma ij is equal to, so basically what we can say when we substitute 5 and 6 in is that because we have the elastic and epsilon PA in all three of these terms, that those terms vanish because of as a consequence of equations 5 and 6. And so we're left with this first term, which will be the integral from sigma ij bar up to sigma ij bar plus d sigma ij, and then that will be d epsilon p times d sigma ij, right? And then the next one will be plus. And remember, on unloading this, all these are constant. These have gone away, and this is actually a constant, right? So it's actually this integral in this third integral is actually dang it, ends up being then the integral from sigma ij bar plus d sigma ij sigma ij a d epsilon p d sigma ij. Okay? Call that equation 7. Okay, so let's look at each of these integrals separately now. So let's go ahead and first let's consider let's consider this first integral. So we'll consider the integral from sigma ij bar up to sigma ij bar plus d sigma ij. And that's going to be equal to d epsilon ij p d sigma ij. Okay? Well, we don't know everything that's there, but the difference here, the delta in sigma, is just d sigma ij. And so we can actually just apply the mean value theorem from calculus here and write that this must be the average plastic strain during this stress increment d sigma ij times d sigma ij, right? Which is going to be the same as, it's something that's of the order of d epsilon ij p d sigma ij, right? So it's a second order in differential quantities. So that's the main feature. Okay, second order in differential quantities. Okay. So what we're going to do with this is actually we're going to show that it's negligible, and we can set it equal to 0. And now we can consider the last integral. Okay, so the last integral, right, that looks like the integral from sigma ij bar plus d sigma ij up to sigma ija. And now it's important to remember that the plastic strain increment now does not change. Just d epsilon ijp times d sigma ij, which we can write as sigma a minus sigma ij bar minus d sigma ij, that quantity times d epsilon ij p. Okay? Call that equation 9. So what we do now is we substitute equations 8 and 9 back into 7. Okay? And remember, 7 looked like the integral around this times epsilon ij d sigma ij, right? That was the first case, is going to be equal to now sigma a minus sigma ij bar times d epsilon ij p, and I'm writing this in this way deliberately, minus d sigma ij d epsilon ij p, and then plus something that's the order of d epsilon ij d sigma ij. Sorry, this is p, right? So what we're going to do is we're going to go ahead and we're going to neglect these second order terms relative, and because this will be the dominant term, so we'll say we're going to neglect the second order terms. We'll call this equation 10. Okay, and so what we're left with is now the following. So we're left with this quantity that the integral epsilon ij d sigma ij around the load path is going to be equal to sigma a minus sigma ij bar d epsilon ij. Okay? P, sorry. Okay. And then what do? We apply the postulate right, that the integral of that quantity that we derived in the last module is less than or equal to 0, to conclude that then sigma a minus sigma ij bar times d epsilon ij p is less than or equal to 0. Or we could write it as sigma ij bar minus sigma a. I should make these similar in my notation. So this should be sigma a ij. This is also ij a. The epsilon ij p is then greater than or equal to 0. So this, they're equivalent statements. This is frequently what's referred to as the maximum dissipation postulate. So we'll call this equation 11 and say that equation 11 is referred to as the maximum dissipation postulate. Okay, so I know you're probably thinking, well, who cares? Well, again, what we're gonna do is use this to demonstrate what's required of a yield surface for plasticity. And so again, we're going to talk about the shape of that yield surface that this leads to, as well as how the strain increment must be related to that yield surface. So those are the kind of the key features that we want to talk about.